You found the skeleton. How would you tell it's a dinosaur? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
Hey there, YouTube, the Dapper Dinosaur here. So, towards the end of May, I had a long phone call with Cindy Lincoln. When I say long, I mean 5 hours ending at 3 a.m. my time, even later for her. We talked about a lot of stuff, science included. One takeaway that I have is that the idea of monophyly is something she is not getting, and perhaps I need to work on something explaining the concept better. However, that is not this video. This video is a response to a video she sent me the next day. It's a video she made a while back about how the geology of the Earth, in her opinion, does not necessitate an age any greater than 6,000 years. I'm going to take a look at this, and since the title of the original video says to try to change her mind, I'm going to try to do this. And do it without having seen the video before. The script is going to be written as it goes, come what may. One final note, Cindy's audio is a bit rough, but I have cleaned it up a bit, as apparently did she. It is what it is. So without further ado, take it away, Cindy.
I promised I would do a video on layers before I got fired from the Science Center.
Here Cindy is talking about the Dinosaur Adventureland Science Center, where she was sent as a punishment away from her garden by Kent Hovind, for the crime of daring to criticize Kent's probable gay lover, Steve.
At Dinosaur Adventureland, I was working on a layers display. The significance of layers is time.
I agree. Of necessity, any layer of any kind that we find in the geological record must have been not formed at some point, taken some time to form, then taken some time to lithify, cool, or metamorphose, as the case may be, and then some time likely passed until we see it today.
I believe that's one of the major ways they say that the Earth is millions of years old, because they say that each layer represents a unit of time, and if there's millions of layers, then there's millions of years.
Not quite. Layers, whether strata or laminae, are not given some single duration over which they must have formed, nor are all such layers formed at a single rate, nor can it be determined just from the form of any given layer how long it was between them. Further, while the age of the Earth was at one time estimated using stratigraphy, such estimates were always minima, and we now rely on radiometric dating. It is true that without radiometric dating, we would not know how old the Earth is, but we would still have a good idea of how young it could be, and that would indeed be millions, if not tens of millions of years.
So, just like this lady here is doing, let's look out into a vast amount of Earth's amazing displays.
Sounds awesome, Cindy. Let's do it.
This is Horseshoe Bend and Antelope Canyon, part of the Grand Canyon. Now, first of all, you can see that these layers go for miles and miles and miles and miles.
This is a bit nitpicky, but you cannot see that from this picture. However, it is true that the strata present in the Grand Canyon are generally very extensive horizontally.
In fact, if we looked at a map of the U.S., you'll see it covers half the U.S. Contrary to what you see in the Grand Canyon, where everything's stacked like pancakes, horizontal, layers are not always found like that.
In fact, even in the Grand Canyon, some of the lowest strata are not actually horizontal. The Vishnu Cyst and the Grand Canyon supergroup, those rocks below the Great Unconformity, are in fact tilted. It's not until we get to the Paleozoic rock that we get horizontal stacking, and even here, it is not perfectly horizontal.
This is pretty amazing. So this is obviously formed in a fluid environment.
That is not obvious. Experiments on rock plasticity go back at least as far as 1910. So for over a century, we have known that under some conditions, normally brittle rock can indeed bend, and this isn't a matter of what Ken Ham might call historical science. This is laboratory work. Humans have caused rocks to bend by simulating the heat and pressure found under the surface of the Earth. This is so well established that I think it's reasonable to simply directly quote Wikipedia on this. Quote, experiments are usually carried out with the intention of characterizing the mechanical behavior of rocks in terms of rock strength. The strength is the limit of the elastic behavior and delineates the regions where plasticity theory is applicable. Laboratory tests for characterizing rock plasticity fall into 4 overlapping categories: confining pressure tests, pore pressure or effective stress tests, temperature-dependent tests, and strain rate-dependent tests. Plastic behavior has been observed in rocks using all of these techniques since the early 1900s. The Boudinage experiment shows that localized plasticity is observed in certain rock specimens that have failed in shear. Other examples of rock displaying plasticity can be seen in the work of Cheetham and Gnurk. Tests using compression and tension show necking of rock specimens, while tests using wedge penetration show lip formation. These tests carried out by Robertson show plasticity occurring at high confining pressures. Similar results are observable in the experimental work carried out by Handon and Hager and Patterson and Mogi. From these results, it appears that the transition from elastic to plastic behavior may also indicate the transition from softening to hardening. More evidence is presented by Robinson and Schwartz. It is observed that the higher the confining pressure, the greater the ductility observed. However, the strain to rupture remains roughly the same at around 1. The effect of temperature on rock plasticity has been explored by several teams of researchers. It is observed that the peak stress decreases with temperature. Extension tests with confining pressure greater than compressive stress show that the intermediate principal stress, as well as the strain rate, has an effect on the strength. The experiments on the effect of strain rate by Cernighetti and Boozer show that increasing the strain rate makes rock stronger, but also makes it appear more brittle. Thus, dynamic loading may actually cause the strength of rock to increase substantially. Increase in the temperature appears to increase the rate effect in the plastic behavior of rocks. After these early explorations in the plastic behavior of rocks, a significant amount of research has been carried out on the subject, primarily by the petroleum industry. From the accumulated evidence, it is clear that rock does exhibit remarkable plasticity under certain conditions, and the application of a plasticity theory to rock is appropriate. End quote. The whole article is linked, and that one section has 10 links to different papers starting all the way back in 1910. The fact that solid rock can plastically deform is not a matter of any controversy. We know for a fact that it can, as solidly as we know that water boils at 100 degrees and freezes at 0 under normal conditions. If this were less well established, I wouldn't just quote the wiki. But in this case, I feel like that's all that demonstrating this very basic, extremely strongly supported fact needs.
And it certainly looks to me like it was not formed one layer at a time.
Here we are running into the problem of looks like. This island looks like a dolphin. This mesa looks like a face. This rock looks like an elephant, and this toast looks like Jesus. The problem is that humans are really good at seeing things that aren't really there, and really bad at figuring out what things really are when they're outside of their daily experience. That's why being a geologist takes years of training. I love Cindy, but the fact is that she is not really equipped to simply eyeball a picture of rocks and know what they are or how they could have formed. And I say that because even geologists are not so equipped.
But this was all moved together when it was fluid, kind of like clay when it's soft and then it gets hard.
Well, they were bent together, that's the consensus of everyone, but that's not the same as being formed together. Layers are formed, then bent as a rule. There are some cases, like at the bottom of a lake that slopes all the way to the bottom, where sediments could be deposited in a non-horizontal shape, but that's the exception.
We find amazing layers from the United States to Israel to China to South America. We're going to see layers all over the world.
One of the things I feel like a fair few young earthers miss on is that geology doesn't have a single model for every broad phenomenon. So let's take a closer look at this particular formation that Cindy's talking about. It's a spot called The Wave in northern Arizona, right near the Utah border. It's administered by the Bureau of Land Management. It's Aeolian sandstone from the Jurassic Navajo sandstone. So let's talk about the Navajo sandstone. In the 1970s, there was some controversy as to whether it was really Aeolian, with some arguing that it looked like known Holocene estuary and shallow marine sandstone. But the well-sorted nature of the formation and its thoroughly frosted particles seem to have settled that debate. It's also known for extensive bioturbation. Combined, these two facts mean that the Navajo sandstone absolutely did not form in a flood. We know this because turbidite erases things like bioturbation, and it does not frost sand grains the way wind deposition does. Now, this is not to say that the sand in the desert never got wet. It did each year in a wet monsoon season, probably in the summer. This is why the layers in the wave are so clear. They are seasonal laminae. Now, as to the folding evident in the wave, they did indeed form when the sediment was unlithified, which explains their extreme smoothness and complete lack of fracturing. But that is not how all folded sediments are. While unlithified folding does well explain this formation, it does not explain many other folds, and further, the stone which is folded itself contradicts a flood model of deposition in many ways. In order for the young Earth flood model to work, it needs to explain all the data, not just one aspect of a given formation, while failing to explain the other aspects.
In massive depths, formed in processes that we don't see happening today.
Yes, because deposition occurs all over the world. But that's one of the problems. We do see these processes today. We have monsoonal deserts today. We can watch rock plastically deform before our eyes. The way we know that rocks are what geologists say they are is because we see the same rocks forming right now. And sure, perhaps there are some rocks that are still mysterious and might be explained by a mechanism that doesn't occur today, such as banded iron formations, which do not form today. But even if we assume that all kinds of rocks that we can't see forming today, we can't know how they formed, what about the hundreds of vertical meters of rock that we know very well how they formed, because we can see the same kind of rock forming? Let's make an analogy. A lot of people have made pancakes. They're simple and delicious. You mix some egg, flour, salt, baking powder, buttermilk, and maybe some other fancy things like chocolate or butter into a batter. Pour it onto an oiled hot surface, and boom. Fluffy, delicious, pan-cooked bread, perfect for spreading syrup, jam, butter, honey, or whatever on. We can watch and even make pancakes for ourselves. It's very easy to observe. But let's say you and a friend go to a restaurant and you order pancakes. Your friend tells you that because the rise in the pancakes could be the result of yeast in an oven, that you're really eating an oven cake. Well, yeah, she is right that yeast can cause a rise in bread, and that this can happen in an oven, but what about every other aspect of the pancake? Everything about it, including the rise, are consistent with how you've made pancakes. And some of it is inconsistent with an oven, like the relative lack of crust and the browning patterns. Should we just conclude that maybe you're eating an oven cake made with yeast? Just because, even though some of the food can't be explained that way, and none of it requires an oven, one aspect of it could be so explained? Of course not. You should conclude that you're eating a pancake, and your friend is ignoring most of the relevant information, as well as the evidence of her own experience, and that of countless others. That's what's happening here. Yes, the folding is, on its own, consistent with a flood scenario, but nearly everything else about the rock is not, and that one aspect does not require a flood.
We might see some flooding that would cover up a town with mud. We might see a volcano that would cover up a town with ash and lava.
We do, and using physics we can scale things up, which is what happened when geologists figured out what caused things like ashfall beds or the channeled scablands, that being a gigantic volcanic eruption and a series of colossal floods, respectively.
But the layers we've seen thus far are sedimentary. That means they're laid down by water, kind of like mud and silt.
No, that is not what that means. It means they are composed of small grains that are cemented together in one way or another. The grains do not need to be laid down by water, and we already saw the Navajo sandstone, which was not laid down by water, but by wind. Something it has in common with the Coconino sandstone from farther in the Grand Canyon. That sediments are always deposited by water is a common misconception I hear from young Earth creationists, but it simply is not true.
And these depths and expanses going for miles, like halfway across the country, that cannot be a local river.
Well, that's true, but that these strata were caused by a single local river is not the model of any of them. Let's just take one formation, the Chinle Formation, a Triassic formation known for its wonderful collection of vertebrate fossils, especially reptiles such as Phytosaurs and Arizonosaurus. We're going to go sort of Arizona themed today, I guess. The Chinle Formation is made of fluvial deposits from braided channels, but across the horizontal extent it changes from near shore and estuary to inland and higher elevation. Further, it's the result of not a single stream or river, but a whole drainage system. In the case of the Coconino and the Navajo sandstone, we have two separate deserts. Deserts can be quite large, just look at the Sahara or the Gobi, both of which cover huge portions of a continent. Or we could look at the Red Wall limestone, which is also extensive and represents a marine environment and was formed when the sea levels were higher. When all the lowest parts of land are under a shallow sea, that's a large depositional environment. So not only are the layers that are so extensive horizontally the kinds of rocks that can form over a wide area, they're also the kinds of rocks that we know do form over wide areas even today.
Here's some layers, also called strata, in Salta, Argentina.
While this picture does indeed show different strata, not all the layers in the Earth are strata. Some are laminae. A stratum represents one consistent but somewhat broadly defined deposition, which comes from a fairly consistent depositional environment. A lamina is a layer within a stratum that results from subtle variation in the deposition, such as seasonal variations or perhaps irregular events such as, yes, a flood. Or perhaps even some other kind of random but significant occurrence.
Notice the different colors. Okay, so if this represents 1 year, 1 year, 1 year, each layer being a year.
Which it almost certainly does. Generally, it takes over a year to simply deposit a large stratum worth of sediment, and between the layers, there is at least some amount of time for deposition to at least stop, and perhaps erosion to occur. And yet, more time for a new depositional regime to take over, producing the next stratum. Generally speaking, the time between strata must, of physical necessity, take many years, often thousands or millions. That's simply because if they formed much faster, then there is no plausible way for the depositional environment to change so radically. And no, a flood does not help, because that is a single depositional environment, and floods do not result in strata, they result in, at best, a single stratum with the characteristics of turbidite. That is, it tends to be highly graded, there are no ichnofossils or other bioturbation, and there's the presence of ripple marks, etc.
Whatever's laying this stuff down on a continent-wide basis changes every year?
No, as a rule, depositional environments tend not to change on a timescale best described with years. We're talking centuries, millennia, or even larger timescales. And we know this because we simply do not see depositional environments regularly changing on the timescale of a year. Sure, it could happen here or there, but that's not the normal way it changes. And when it does happen that quickly, it's usually because of an identifiable catastrophe, like a volcanic eruption, which may leave behind a tough stratum, and then on top of that, a new depositional environment may take over. But as a rule, it is not realistic to assume a timescale as short as a year to explain the transition between strata.
So that some years it's pink, some years it's adobe clay colored, some years it's turquoise, some years it's tan. And Kent Hovind always says, where are these layers coming from?
Interestingly, the origin of the sediments in a layer is something that can often be assessed. For example, some sandstone is called feldspathic, as in the Navajo sandstone that we started this video with. That means that the grains are eroded from feldspar, a kind of igneous rock. Sometimes the grains themselves are from older sedimentary rock, perhaps rock that even still exists higher up in the column in other locations. Essentially, the layers came in the past from other rocks, and this must be true under a flood model as well, unless we want to say that all the sediment was a direct miraculous creation by God after creation week.
And when you find marine deposits in the layers, or even dinosaurs in the layers, you know it was laid down by water.
Now, as we have already gone over, many rocks containing fossils are not laid down by water. We've already seen the Aeolian Navajo sandstone, but there is also subaerial ash or tuff. There is also evaporite, which is a special kind of deposit that is made by water, but not by water flowing like in most marine or fluvial deposits, but rather by standing water evaporating, leaving behind non-volatiles such as salt.
We don't see water going over half of a continent today.
No, but we do see deserts covering large portions of continents, as well as drainage systems such as the Orinoco and the Amazon drainage system, and we have extremely large marine depositional environments offshore today. So we do see the same kind of widespread deposition today. It's just not happening in the low-lying interior portions of modern continents, because we're in an ice age, where those parts of the continent are above sea level. So this complaint comes down to, how can you say that there was a large-scale marine deposition in continental interiors in the past if there is no widespread marine deposition on continental interiors today? And their answer is that we can see the same deposition offshore. And if you want to introduce a new cause for the same rocks, you're going to need a reason why your cause better explains all the data, including the data from inland marine deposits, like the Bright Angel Shale.
That's the only way you could bury a dinosaur, is in fluid mud.
Also incorrect. One of the more famous dinosaur fossils, the so-called fighting dinosaurs, with a protoceratops and a velociraptor locked for all time in mortal combat, was an Aeolian sandstone, and was most likely caused by a landslide. Now, most dinosaur fossils are indeed in waterborne sediment, but it's not all.
Again, I'm open to respectful communication about all this.
Well, I hope this counts.
Now, this is really interesting. A stratified island near La Paz, Mexico. Again, you'll see it certainly doesn't look like the layers represent a unit of time.
A unit? No, but they must have taken some time to form, even under a flood model. But let's see what we can learn about this island's geography. This island is part of Islas Espiritu Santo, and it's Mexico's 11th largest island by area. The name means Holy Spirit Island, in case you're curious. So the best information I can find on the island is in Spanish, which makes sense for a relatively small island in Mexico that has little economic significance beyond ecotourism of the water surrounding it, Luckily for me, I can read Spanish reasonably well. So this island is primarily volcanic in nature with layers of tuff, basalt, and basaltic conglomerate, with olivine heavy rocks as the youngest in the group. It has been uplifted from the floor of the ocean because of tectonic activity, specifically earthquakes along the San Andreas Fault's southern extent. Now, basalt, which makes up a large portion of this island, can and does indeed form quickly. In fact, it characteristically both flows and cools quickly, as it is made from low viscosity lava. But the tuff has to take time to lithify before new lava can flow over it without just mixing into that lava, and we have layers of distinct tuff at Isla Espiritu Santo, and the distinct layers of basalt. So it would be very difficult to explain the formation of the island in only a single year. That being said, the whole island is fairly young, and geologically speaking, probably did not take very long to form. But that is not something you can ascertain just by eyeballing the strata of the island.
The other layers we saw were small. This is a huge layer. Is this all one amount of time because it's all the same material?
That's a great question. Assuming that Cindy is talking about the top layer of tuff, it was in fact probably all deposited during a single eruption of one or a few related volcanoes. A single stratum by definition represents a single depositional environment. Now in the case of tuff, that environment is ashfall, and yes, that probably represents either a single eruption or several eruptions over a relatively short period, such as decades. But it is not as simple as noting that a stratum exists, and then measuring its vertical extent, and then just assuming a deposition rate. Each stratum must be examined to see what kind of rock it is, whether the system that deposited was high energy or low energy, as well as what kind of sediments are laid down and how quickly such things can happen. Now, tuff, being primarily volcanic ash, is sort of like a mix between sedimentary and igneous rock. It is composed of grains that come directly from a volcano, but it is also deposited and lithified in the same manner as a sedimentary rock. So, the answer as to whether a single stratum signifies a period of time, which I'm assuming is what Cindy meant, rather than a unit of time, is yes, but each stratum is unique and requires a different amount of time to form.
And whatever laid it down for the bottom layer was sure a lot different than the top layer.
Yes, it was. One was a lava flow of liquid rock that was weathered into chunks, then cemented underwater. The other was light, low-density ash particles raining down. At least that's based on the work of the geologists that started work here in the 1980s. And admittedly, that work is not in my first language, or even my third. Spanish could reasonably be called my fourth language, so hey, check the PDF I linked. Maybe I'm way off.
No, I don't think these layers represent time.
Well, lithification takes time, and that tuff lithified, so the ash that fell to make it had to have done so a while ago. And on top of that, it had to fall after the basalt had cooled, eroded, and cemented into conglomerate, so we have a minimum. Now granted, it's not a very long minimum. Lots of igneous rock can be deposited quite quickly. But the existence of quick-forming rock doesn't simply override the existence of slow-forming rock. That's kind of like noticing that mice typically only live a few years, and then concluding that's how all animals work. And no animal could be over 5 years old, or it would have died by now.
To a certain degree, you could say, if water is laying things down, whatever goes down on the bottom is occurring in time before whatever comes on top of it later.
Yep, that's called the law of superposition. Sediment can't simply teleport under rock in order to be deposited under already existing rock. So in undisturbed sedimentary sequences, the higher strata are younger. Now, there are areas where this does not work. For example, an igneous intrusion happens when liquid magma pushes into an already existing older rock, so the younger igneous rock is now lower than the older rock. Or we can have folding such that the rock layers are near vertical, and work must be done to figure out the direction of folding, and so which end of the now nearly vertical strata is the older end. But yes, the law of superposition is indeed simply derived from the common sense notion that if you're dropping bits of rocks in layers by fluid, you can't drop those layers under already existing layers.
But that doesn't mean anything similar to a reliable clock.
That's true, and stratigraphy on its own is not used to get absolute dates for that reason. At best, it can give us an estimate of the minimum age of a group of rocks, but that's it. Instead, stratigraphy gives us relative ages. It tells us the stratum A is older than B and younger than C, but not by exactly how much. For absolute dating, we turn to things like radiometric dating. Based only on stratigraphy, we could probably estimate that the Earth is at a minimum many tens of millions of years old, but we absolutely could not pin that down to the approximately 4.5 billion years that other dating techniques can give us.
Or even, may I say, the geologic column.
I'm not really sure what Cindy means here. If you're watching, Cindy, feel free to let me know.
This, as well as some of the really fine layering, doesn't look at all like the geologic column.
Well, the geological column isn't a physical thing, it's a model. It's a sequence in which the rock layers of the Earth are arranged in order with oldest at the bottom and youngest on top, and none are skipped over. This is done because, while in almost no locations can you see a continuous record of deposition for the whole column, the order of the strata is never violated anywhere after accounting for things like folding and upthrust that can make the layers vary from horizontal, or areas where deposition occurs on subhorizontal surfaces. The model helps orient us in geological time when we are looking at real rocks. A similar model is the celestial sphere. In astronomy, we talk about the sky as if it were a solid sphere over the Earth at some indeterminate distance above the surface. It has a coordinate system of latitude and longitude, with the equator being a projection of Earth's equator, such that if you're directly on Earth's equator, then the celestial equator is directly above you, and a prime meridian at the point of the vernal equinox. The location of stars, nebulae, planets, etc. are given by reference to these lines of latitude and longitude. But the thing is, the celestial sphere doesn't really exist. It's a useful model that humans can use to orient themselves in terms of the night sky. So you should no more expect to see the geologic column in a real-life set of rocks than you should expect to see the celestial sphere's lines of latitude and longitude when you look at the night sky.
We're going to see a whole lot of variation. The picture that normally is seen of the geologic column doesn't look anything like what we're about to see all over the world.
Well, yeah, it's an idealization used as a reference point. It was not intended to look like any particular set of actual rocks.
Here's another really skinny one, like the Antelope Canyon had those really fine layers.
Those aren't strata. Those are what will become laminae in unlithified sand. And you can tell it's unlithified because someone shoved a penny in there for scale. These are moissanite placer deposits containing high amounts of rare earth elements. Basically, upstream from this deposition is something being eroded, since that's how deposition works. These bands are the result of some rocks high in rare earth elements being eroded, that heavy sediment was carried to where the sand is being deposited now, and it's now in the sand. I honestly don't know what conclusion we can draw that's relevant to the age of the Earth, or the age of any rocks in particular. It doesn't even tell us the deposition rate of this sand, and in the paper it's from, which is in the description, doesn't tell us either.
As opposed to the one we just saw in La Paz, Mexico, that had the huge fat layers.
Well, in Mexico we were looking at strata, and here we're looking at what will become laminae if the sand lithifies. Laminae are contained within strata, so they must generally be smaller than strata. You can think of strata like a bunch of books stacked on a table. Each one is a distinct work, and noticeably different from the next. The laminae are like the pages, still distinct, still layers, but clearly each is part of the larger, distinct book, and mixing up pages with books is a serious mistake.
Notice the penny at the bottom right. That's to give you scale. And then if we read, it says heavy minerals, the dark layers, as a thin strata in beach sand.
I don't know who wrote that caption, but that's not what the source says. The actual caption says, heavy mineral rock layers, black sand, in a quartz beach sand, Chennai, India. It doesn't call these strata because they aren't strata.
This is in India. Do those different color stripes represent time?
Well, kind of. Because they are from a distinct period of weathering, they couldn't have occurred simultaneously with the rest of the weathering that caused the rest of the sand both above and below, especially since if that much sand was deposited in a single short time, it would have to have been a high-energy event. And so, rather than getting a few neat layers of high-density minerals, the sand deposit would have been graded, with all the heavy layers at the bottom. So, while I don't know how much time these layers represent, yes, they of physical necessity must represent a continuous event occurring over some period of time, not a single inundation that dumped a large layer of sand.
In a way such as like a dating kind of time?
Well, this is unlithified, so it couldn't have happened all that long ago. But on its own, no, we can't absolutely date sandstone. However, we could relatively date it, and given its character, we could give some kind of minimum estimate. So we know it didn't happen in a day, but it also probably didn't take 10 million years to deposit. Of course, sandstone has a wide range of deposition rates, so it's hard to estimate how long a formation took to deposit just by knowing it's made of sandstone.
Yes, the bottom would go down first and the top would go down last in many instances, unless, like Kent says, there's horizontal deposition from rapidly flowing water. But that's not the kind of time that you could date history with.
Agreed, and that's why no one does.
We don't know when the flow happened that laid this down.
Well, we know it had to be fairly recent, but that's geologically speaking, so it could have been a few years or a few millennia ago.
Okay, now we're going to go from India to New South Wales, Depot Beach. Just noting the difference in sizes and texture. This is not sand, this is rock.
It's not easy to find information on Depot Beach specifically, but Depot Beach is part of the Sydney Basin, which is an area with rock stretching from the late Carboniferous to the early Cretaceous. So let's see what Cindy has to say about it.
Now, a lot of the rock layers, especially in the Grand Canyon...
I'm really hoping I didn't spend all that time trying to figure out the stratigraphy of Depot Beach just to go back to the Grand Canyon. Don't do this to me, Cindy!
And if you look at a chart of the geologic column as given in books, most of the layers are limestone.
I'm going to need to see a citation on that. The geologic column in textbooks usually just has layers listed by system name, such as Hadean, Cambrian, Cretaceous, Eocene, etc., and depending on how specific it is, it might have stages too, like Norian, Radian, or Maastrichtian. But these systems are associated with many kinds of rock, like siltstone, sandstone, shale, greywalk, basalt, and yes, limestone, though that list is far from exhaustive.
Limestone is calcium carbonate, which is how they make cement.
So this is kind of true and kind of false. Calcium carbonate is an ingredient in cement the same way that sodium and chlorine are ingredients in bread. Sodium is a soft white metal that reacts violently in contact with water by catching fire and exploding. Chlorine is a noxious, toxic gas that can cause severe chemical burns and death in high concentrations. So how is it that bakeries are anything but death traps? Well, because these elements aren't used directly. They're used in the form of sodium chloride, aka table salt. Similarly, calcium carbonate is burned in kilns to produce calcium oxide, or quicklime, an entirely different molecule. As a result, carbon dioxide is also produced, and the cement industry is directly responsible for about 10% of all man-made CO2 emissions worldwide. This is done in the production of both hydraulic and non-hydraulic cement. Now, concrete is essentially an artificial rock made by mixing together stones with cement, and in the past some concrete did use limestone directly, but this is no longer done because limestone erodes quickly in acidic conditions, and the rain is still acidic relative to before significant boosts to atmospheric carbon by humans, but even then it was used as bits of rock that the cement is holding together.
So you can have a mud flow that turns to rock.
But that would be mudstone, not limestone. Limestone is composed primarily of granules that originate as the shells of microscopic plankton, not mud, which is primarily made of silicates usually. And there's a reason why the thing that becomes limestone isn't just called mud, it's called limey muck or limey mud. They are not the same thing. Normal mud flows will never become limestone.
You can see this used to be like mud. It used to be fluid.
Oh good, I did not waste my time looking up the stratigraphy of Sydney Basin. Well, let's start at the bottom with the Loch Navar Formation, which is made of late Carboniferous igneous rock. So definitely not mud, but in some cases liquid, yes. As in liquid hot magma. Really lava, but then I couldn't make the joke. Give me a break. I'm going to skip a few minor members that only exist in small areas. So next we have the Rutherford Formation. This is composed of fine-grained conglomerates associated with sandstone, siltstone, mudstone, and shale. So only parts of it are consistent with the idea of flowing mud, most of it is not. Next up is the Farley Formation, which is later, but of the same basic composition as the Rutherford Formation. Next we come to the Braxton Formation, which is composed of lithic sandstones, minor conglomerates, and siltstones. So no mud flows here. And that's about as high as this beach goes, although other parts of Sydney Basin do go higher into things like the Mulbring and Dempsey formations. So whatever it might look like to a casual observer with no training, such as myself or Cindy, this formation cannot simply be the result of mud in a single flood. It's the result of dozens of depositional environments, few of which are consistent with a high-energy event like a flood.
But now it's rock. And the presence of limestone or calcium carbonate,
which, near as I can tell after looking up the stratigraphy of the area, is not present, and even if it were, it's calcium oxide that is the direct component of cement, not calcium carbonate, as Cindy seems to believe.
is oftentimes what cements the mud.
Actually, in terms of carbon-bearing cementing agents in nature that cement mudstone together, it's far more often gypsum, that is calcium sulfate dihydrate. The other common cementing agents in mudstone are pyrite and barite. Pyrite is iron disulfide, and barite is barium sulfate. I think we can see that the common component isn't actually even carbon, it's sulfur. Now, outside of mudstone, calcium carbonate is indeed a cementing agent, as are silica and hematite or red iron oxide. But remember, even when calcium carbonate is the cementing agent, we're not talking about the quick-setting artificial human product. Humans don't directly use calcium carbonate because on a human timescale it's useless as a cementing agent, meaning it's also useless on a timescale of a few days to months, which is what is required for lithification under a flood to allow for distinct strata within a year-long inundation.
Silicas also can be a cementing agent.
That's true.
Silicas come from volcanic sources.
Ultimately, yes.
Calcium carbonate comes from marine sources, such as crushed up shells and crushed up coral. It makes a really fine powder when it's crushed up.
Those are sources, yes, but compared to the shells of microscopic organisms such as coccolithophores and diatoms, the shells of macroscopic organisms are a fairly minor component. But I'm not really sure if this is relevant.
And it's also known as chalk.
Yes and no. Particularly fine-grained limestone is chalk, but not all limestone is chalk.
The Cretaceous period, Crete, the island of Crete, Cretaceous. Crete means chalk.
Again, partially right. The Cretaceous is indeed named for chalk, but the island of Crete is not. Its etymology is unclear, and it might even derive from the ancient Minoan civilization, or from ancient Luwian, an enigmatic and possibly Indo-European language from Anatolia. There are both Paleozoic and Mesozoic limestone formations in Crete, but it's not like those are the dominant rocks in Crete. A lot of it is evaporites, fluvial sandstones, etc., which also occur there. Also, interestingly, evaporite forms when bodies of water evaporate, the kind of thing you're not expecting in the middle of a worldwide flood. So I would love to see a good explanation of how they formed underwater in the middle of part of a flood, then stopped forming, then had more sediment deposited on them, all underwater. All that being said, the topmost layers of the sedimentary rock on Crete are indeed chalky, so it's not so much that it's wrong as it is to say it's far more complicated than just saying Crete has cliffs of chalk.
There's a lot of chalk cliffs in this world, including in Crete.
Well, for the most part, they are not crushed. They are intact microscopic shells that are already fine powder. So for the most part, nothing caused that, because it's not primarily what limestone is. But also compaction can crush up larger shells, and in limestone, the crushed shells of living things like bivalves and coral are usually not ground into a fine powder, which is how we can actually recognize them as being the crushed parts of these organisms. Rather, they are broken into macroscopic chunks that are incorporated into the limestone.
You have to ask yourself, what would cause shells to be crushed into a fine powder?
The fact that the same process can be observed in different parts of the world does not imply on its own a worldwide process. And the fact that there are areas where this process is not evident at all means it was very unlikely to actually be a global phenomenon that caused this. But I think this is where I'm going to end this part of this. If you like this video, remember to hit like, and if you hated it, hit dislike, and tell me what I got wrong, or why you hate it. I'm the Dapper Dinosaur. Before you go, I want to take a minute to thank my patrons and channel members, especially those pledging $20 or more. Work in Progress, Benthoven, Cynically Skeptic, Denny5252, Ian Chen, John Ackerman, Landon Knoll, Iapetus, Mabbity Babbity, Sphincter of Doom, Starrunner, and the Venerable Bean. Without my channel members and patrons, this channel simply wouldn't exist as it does now. You certainly wouldn't be getting up to 3 videos a week. You'd be lucky to get 1. So, if you're interested and you can afford it, check out my Patreon link in the description below, or the Join the Channel button. Both of them get you access to the special patron and member-only Discord server, where I like to hang out. And at higher tiers, you can also get access to other things like your names in this credit, video requests, and more. No matter how much you pledge, you always get early access to my videos, and as of the time of this recording, that's about 10 different videos that you could have access to. If a monthly pledge isn't right for you, there are always other ways to support the channel. I have a merch store linked in the description. There's also an Amazon wishlist linked there. And if none of that's right for you, and you just want to support the channel without spending any money, just liking these videos, commenting, and sharing them on social media goes a long way.